Good day, this is Professor Will, CBMD PhD. Today's Friday, August 28, 2020. It is 5:26 and 27 seconds a.m. Eastern Standard Time, and this is a continuation of my research. But before we get started, let's take a look at something I wrote. In today's video diary, I would like to talk about one of my past ideas. In the early millennium, I had an idea, a revelation of engineering a microchip interface that operated on photons, that being light. On the other hand, my insight into the past-dated functioning electron IC was like a bank of permutations, that being squeezed or depleted of its performance and resources, devices and modern-day peripherals. Meaning, electronic microprocessors are simply going towards multiple processors, which we are now limited towards potentials. In other words, we have a lot of electronic created heat in modern days, and not enough space for performance to allocate combinatorics. I had ideas to build my own experimental and modeled prisms to solve the optical photonic and grid continuities. I had yet to solve the light integrated chip problems, yet shortly after I found similar ideas on the World Wide Web, in early 2000-ish. I shortly recognized, since the concept was already in proprietary publication, I neglected the project and went on to hierarchical tangents of research. Well, I hope my audience enjoyed my presentation. Hope to see you again. Until next time, let's continue on with my astronomy and quantum research. Ancient star explosions revealed in deep-sea sediments. Date August 25, 2020. Source Australia National University. Summary. A mystery surrounding the space around our solar system is unfolding thanks to evidence of supernova found in deep-sea sediments. Researchers show Earth has been traveling for the last 33,000 years through a cloud of faintly radioactive dust. These clouds could be remnants of previous supernova explosions, a powerful and super bright explosion of a star. The researchers searched through several deep-sea sediments from two different locations that date back 33,000 years using the extreme sensitivity of HIAF's mass spectrometer. They found clear traces of the isotope iron-60, which is formed when stars die in supernova explosions. Iron-60 is radioactive and completely decays away within 15 million years, which means any iron-60 found on Earth must have been formed much later than the rest of the 4.6 billion year old Earth, and arrived here from nearby supernovae before settling on the ocean floor. Researchers previously found traces of iron-60 at about 2.6 million years ago, and possibly another at around 6 million years ago, suggesting Earth had traveled through fallout clouds from nearby supernova. For the last few thousand years, the solar system has been moving through a denser cloud of gas and dust, known as the Local Interstellar Cloud, LIC, whose origins are unclear. If this cloud had originated during the past few million years from a supernova, it would contain iron-60, and so the team decided to search more recent sediment to find out. Sure enough, there was iron-60 in the sediment at extremely low levels, equating to radioactivity levels in space far below Earth's natural background levels. And the distribution of the iron-60 matched Earth's recent travel to the local interstellar cloud. But the iron-60 extended further back and was spread throughout the entire 33,000 year measurement period. The lack of correlation with the solar system's time in the current local interstellar cloud seems to pose more questions than it answers. Firstly, if the cloud was not formed by a supernova, where did it come from? And secondly, why is there iron-60 so evenly spread throughout space? There are recent papers that suggest iron-60 trapped in dust particles might bounce around in the interstellar medium, so the iron-60 could originate from even older supernova explosions, and what we measure is some kind of echo. More data is required to resolve these details. Cosmic rays may soon stymie quantum computing. Building quantum computers underground or designing radiation-proof qubits may be needed, researchers find. Date August 26, 2020. Source Massachusetts Institute of Technology. Summary. Infinitesimal low levels of radiation, such as from incoming cosmic rays, may soon stymie progress in quantum computing. The practicality of quantum computing hangs on the integrity of the quantum bit, or qubit. Qubits. The logic elements of quantum computers are coherent two-level systems that represent quantum information. Each qubit has the strange ability to be in a quantum superposition, carrying aspects of both states simultaneously, enabling a quantum version of parallel computation. Quantum computers, if they can be scaled to accommodate many qubits on one processor, could be dizzyingly faster, and able to handle far more complex problems than today's conventional computers. But that all depends on the qubit's integrity, or how long it can operate before its superposition and the quantum information are lost. A process called decoherence, which ultimately limits the computer runtime. Superconducting qubits, a leading qubit modality, today have achieved exponential improvement in the key metric, from less than 1 nanosecond in 1999 to around 200 microseconds today for the best performing devices. Researchers have found that qubits' performance will soon hit a wall. Researchers report that the low-level, otherwise harmless background radiation as emitted by trace elements in concrete walls and incoming cosmic rays are enough to cause decoherence in qubits. They found that this effect, if left unmitigated, will limit the performance of qubits to just a few milliseconds. Given the rate at which scientists have been improving qubits, they may hit this radiation-induced wall in just a few years. To overcome this barrier, scientists will have to find ways to shield qubits in any practical quantum computer. From low-level radiation, perhaps, by building the computers underground or designing qubits that are tolerant to radiation effects. These decoherent mechanisms are like an onion, and we've been peeling back the layers for past 20 years. But there is another layer that, left unabated, is going to limit us in a couple years, which is environmental radiation. This is an exciting result, because it motivates us to think of other ways to design qubits to get around this problem. It is fascinating how sensitive superconducting qubits are to the weak radiation. Understanding these effects in our devices can also be helpful in other applications such as superconducting sensors used in astronomy. A cosmic effect. Superconducting qubits are electrical circuits made from superconducting materials. They comprise multitudes of paired electrons known as Cooper pairs that flow through the circuit without resistance and work together to maintain the qubit's tenuous superposition state. If the circuit is heated or otherwise disrupted, electron pairs can split up into quasi-particles, causing decoherence in the qubit that limits its operation. There are many sources of decoherence that could destabilize a qubit, such as fluctuating magnetic and electrical fields, thermal energy, and even interference between qubits. Scientists have long suspected that very low levels of radiation may have a similar destabilizing effect in qubits. In the last 5 years, the quality of superconducting qubits has become much better, and now we are within a factor of 10 of where the effects of radiation are going to matter. Researchers teamed up to see how they might nail down the effect of low-level environmental radiation on qubits. Researchers are designing experiments that shield against the smallest source of radiation to be able to see neutrinos and other hard-to-detect particles. Calibration is key. Researchers first had to design an experiment to calibrate the impact of known levels of radiation on superconducting qubit performance. To do this, they needed a known radioactive source, one which became less radioactive slowly enough to assess the impact at essentially constant radiation levels, yet quickly enough to assess a range of radiation levels within a few weeks, down to the level of background radiation. The group chose to irradiate a foil of high-purity copper. When exposed to a high flux of neutrons, copper produces copious amounts of copper-64, an unstable isotope with exactly the desired properties. Copper just absorbs neutrons like a sponge. Researchers then went on to irradiate 2 small disks of copper for several minutes. They then placed one of the disks next to the superconducting qubits in a dilution refrigerator at temperatures about 200 times colder than outer space. They measured the impact of the copper's radioactivity on qubits coherence while the radioactivity decreased, down toward environmental background levels. The radioactivity of the second disk was measured at room temperature as a gauge for the levels hitting the qubit. Through these measurements and related simulations, the team understood the relation between radiation levels and qubit performance, one that could be used to infer the effect of naturally occurring environmental radiation. Based on these measurements, the qubit coherence time would be limited to about 4 milliseconds. The researchers then removed the radioactive source and proceeded to demonstrate that shielding the qubits from the environmental radiation improves the coherence time. To do this, the researchers built a 2-ton wall of lead bricks that could be raised and lowered on a scissor lift to either shield or expose a refrigerator surrounding radiation. Every 10 minutes and over several weeks, students in the research lab altered pushing a button to either lift or lower the wall as the detector measured the qubit's integrity or relaxation rate, a measure of how the environmental radiation impacts the qubit, with and without the shield. By comparing the two results, they effectively extracted the impact attributed to environmental radiation, confirming the 4 millisecond prediction and demonstrating that shielding improved qubit performance. Cosmic ray radiation is hard to get rid of. It is very penetrating and goes right through everything like a jet stream. If you go underground, it gets less and less. It is probably not necessary to build quantum computers deep underground, like neutrino experiments, but maybe deep basement facilities could probably get qubits operating at improved levels. Going underground isn't the only option. Researchers have ideas for how to design quantum computing devices that will work in the face of background radiation. If we want to build an industry, we'd likely prefer to mitigate the effects of radiation above ground. We could think about designing qubits in a way that makes them rad-hard and less sensitive to quasi-particles. So design traps for quasi-particles so that even if they are constantly being generated by radiation, they can flow away from the qubit. So it is definitely not game over. It is just the next layer of the onion we need to address. Good day, this is Professor Will, CBMD PhD on Astronomical and Computer Science. Well, hope you enjoyed listening. Until next time, have a great day.